Alright, hell yeah. So one of the subscribers sent me this problem to do. And hopefully I'm doing the right one. This is supposed to be out of the Pathfinder. It's question 15. It's check your understanding. And it's a related rates problem. And so I'm going to read through and then I'm just going to show you like the way that I would do a problem just so I know I can get to the solution. I think everybody wants the answer, you know what I mean? And so I'm going to show you a way to get there that probably makes the most sense. I've not done this problem. I've not even read this problem. Okay, hell yeah. So a traffic policeman on his motorcycle leaves the police station. So I'm just going to say, here's the police station, and starts chasing a car which has a time of 2 minutes head start. Okay, so this car passes the police station, and then let's say the police station witnesses, hey, this car's speeding. 2 minutes later, the police officer gets in their car and then starts to move. And so I would assume that the person on the motorcycle is going to be moving at a constant speed. Alright, so let's read. And you should do that with textbooks. Like, it's always, well, I don't know, sometimes kind of guess what you think's going on, and then read the next sentence. Okay, so it says the car, and this is what I don't like about, just like the written, I've been reading a novel, and it's really hard to get into the writer's writing, because like a traffic policeman, so the policeman's on his motorcycle, my bad, and he's chasing a car. See, that's why I was just like, you should be telling the car speed. I have a hard time with cognition, well, that too, but what do you call it? When you're trying to figure out like what the words mean. Anyway, so hell yeah. So the car is the one that's speeding, and the car maintains a constant speed of 60 and 60 kilometers per hour. This is where you could change this to meters per second. Like, I would prefer meters per second, but whatever. Hell yeah. So cool, that's going to be this. Because if we do it, I don't know. Because at some point, I just said, like, how am I going to do this to make it easy? At some point, I want to use units where, and if I say, hey, let's say 10 seconds goes by, like, where is the car and where's the policeman? And then another 10 seconds, where's the car, where's the policeman? And then are they even getting closer together? Because the problem is going to say, I'm just assuming, determine the distance from the police station where the car and the motorcycle will be side by side. That's basically where the policeman on the motorcycle finally catches up to the speeding car. And so, there's a chance that the policeman isn't going fast enough, and the car is just outrunning this policeman, and they'll never meet side by side. Maybe if it wraps around the earth, you should always be thinking outside the box. Anyway, okay, so that's why I would change the units. You know what I mean? And almost right away to get this to meters per second, because it's harder for me to think in portions of an hour. If I said, hey, in 0.1 hours, what would that mean? This person is going to be 6 kilometers away. Well, even if I take that big of a gap, maybe the policeman is now way past, so I do like to solve problems and just like, hey, what I call it is like, hey, run it for 1 second. So, and for a lot of problems, especially involving kinematics, whether you drop something off a cliff, or you have a projectile in motion, or you have two objects that are moving, like if you run it for a second, that's a tangible time, like 0, 1, and that's a tangible time for things to move to different locations. And in our mind, it's kind of easy to quantify what a second is and then how things change. All right, hell yeah. Okay, so in a second here, I might be wanting to change these units. But the car is, let's say the car's speeding, it's going too fast at 60 kilometers per hour. And the policeman on a motorcycle can go much faster and can catch the car, because the motorcycle can go 80 kilometers per hour. And then it says, assume they travel along a straight, busy road. Determine the distance from the police station where the motorcycles be side by side. Cool. And then even this comes up all the time in velocity and acceleration problems. Typically, sometimes they ask, like, what's the distances involved? And so, so right now, we're going to figure out the first, kind of intuitive thing is if the policeman waits 2 minutes, you know what I mean? And how much is 2 minutes? We would do factor label method. I would do 1 minute downstairs. Equivalent, it's going to be 60 seconds. And I would have 2 times 60. It's 120 seconds. Okay, this is why I want to change these speeds. And let's do that right now. So if I have 60 kilometers per hour, I'm going to use the factor label method to change these units. So I'm going to put 1 kilometer downstairs, and then upstairs is the equivalent. So if I put on a side right here, if I say 1 kilometer is equivalent to 1,000 meters, I can write it like this. And then just know that you can stack this like this, or you can stack it like this. And then this is your equivalent ratio. And you know what I mean? I'm sure it seems like there's more to it, but it does change units. So there you go. So the units cancel. And so now I have 60,000 meters. And still have hours down here. We need to change that. So 1 hour upstairs. You could say 1 hour is 60 minutes. And then 1 minute is 60 seconds. Or you could just say 1 hour is 60 times 60 is 3,600. This 6 times 6 is 36, the 2 zeros. 60 times 60 is 3,600. This one you just should put into your memory bank. If simple, I don't know, sometimes this doesn't feel simple to me. 60 times 60 is 6 times 6 is 36. 10 times 10 is, those 2 zeros. So, hell yeah. Alright, so, and cool. So then if we do that, this is how many seconds are in an hour. And then the hours would cancel, and we're left with meters per second. Let's cancel this hour, these minutes, and we're left with meters per second. And so this works pretty good. The 60s cancel, and one of them does. This is where I'm going to run into issues. So we have 1,000 divided by 60. This is 100 divided by 6. And then it's just good to guess. Like, what is 100 divided by 6? I don't know. 100 divided by 5 is 20, so it's a little bit less than 20. Cool. 100 divided by 8 is 12.5, so it's in between 12.5 and 20. Is it 16.66? Is that what it is? So we have, and my calculator is going to die, but 100 divided by 6 is 16.6. Alright, hell yeah. And then so we're going to do the same thing for 80 kilometers per hour. We'll go a little faster on this. 1 kilometer, 1,000 meters. See, and I don't like to write it like that. 1 hour downstairs, so we're going to cancel the 1 hour upstairs with 3,600 seconds. And what should we do here? So we're going to cancel out those 2 zeros, those 2 zeros. We're left with 800. And I shouldn't be doing this, but whatever. 36. What does that go? What does that go to? Yeah, holy hell. Let's for the sake, let's just do this. So we got 22.2. And this meters per second. And we're going to be guessing anyway. I can round this to 17. I can round this to 22. Okay, hell yeah. And but let's I'm going to store this into my calculator, Because what is this? This is the car. So I'm going to store this as the letter C. So we have 16.6 repeated, stored as the letter C in my calculator. This is the motorcycle. So we got 22. I'm going to store that as alpha M. On the TI-83, you push the alpha key and then the letter M. Okay, so after 2 minutes, and then I'm just going to store this as the time. So 120 stored as alpha T. But yeah, so after 120 seconds, each second, so this is just like, you know what I mean? Velocity is, you know, what is velocity? Velocity is a change in position, change in time. You know, some books will write this change in P, you know, change in T. But if you're doing X, Y coordinate system, you know, and then here's the ground, and here's the cars, and then here's the motorcycle, you know, this is going to be your X direction. So this is going to be a change in the X direction and some sort of change in time. Now this is going to be average velocity, where the instantaneous velocity is going to be where the change in time gets so small that it becomes like a dt, where the change in time, you know, approaches 0. And but for constant velocity, you know what I mean, it's going to be the same. Average velocity is going to equal instantaneous velocity because you don't have any change in velocity. Alright, and it's just so fascinating that even like right now looking at this, I don't know. Like, well, now I do know. Actually, now that I have it broken down to here, I'm closer to getting an intuitive guess. But from this problem statement, I couldn't tell you like whether it's going to take 2 minutes, and you know, this person has a 2-minute head start. I don't know if it's going to take 10 minutes, you know, 10 hours. I have no idea. You know, like my ability to intuitively guess when the motorcycle is going to catch the car isn't there. But now that I changed the units on the speeds to 16, you know, let's just call this 17 meters per second and 22 meters per second. Now we're working with something. Okay, so after 120 seconds, the car is going to be a distance away. Every second is going to be 17 meters farther. So we're going to go 17, and then is it 34? Is it 17 times 2 is 34? My brain's not working very good tonight. But anyway, so hell yeah. So after 2 seconds, this thing's going to be, is going to be 34 meters away. And then after, and so that's just after 2 seconds. Okay, so let's figure out an equation. And well, let's just say that's 100 seconds. Don't we just move this decimal place too? So even right off the bat, I can be like, well, this should be, you know, the answer should be pretty close to that, but plus 20 extra. So I don't know. I mean, it could be 1,800 meters away. But let's do this equation first. And so we're going to have 16.6 repeated, which is, you know, 100 divided by 6. And this is the speed in meters per second. Now this is where I use like the units are the equation. I don't know. I have a velocity in meters per second. So I'm going to say here's my units on that. I have a time in seconds. What do I need to do to these to get the distance? Distance is what I want. Distance is upstairs here. Seconds is downstairs. Seconds is upstairs. I'm just going to multiply those together. Hell yeah. And you know what I mean? I like to do that even though some things are intuitive. If I have a velocity, an average velocity, and then I multiply by the time, that's going to give me distance. It's probably the most intuitive equation because we use it all the time. I'm going 60 miles per hour and I'm going for an hour. So 60 times 1 is 60 miles. Okay, hell yeah. Alright, hell yeah, I got some ice water. That felt good. Okay, so let's do this equation. And we're going to multiply by 120 seconds. That is the 2-minute head start. So we're looking pretty good there. 100 divided by 6. And we were just going to store that as alpha C. So we have alpha C times 120, which was alpha c times alpha t. So the car has a 2,000 meter head start. Now this is where maybe we can see, like I see right now, that, you know, like, but let's say this, you've never done like a relative velocity problem, you know. I mean, because, okay, so here's one way to think about it. If you have two people, like, running the 100-yard dash, and then we know just the Earth is, like, moving, you know, let's say they're, like, the sun rises in the east. Is that true? So we're moving towards the east. You know, the sun's, let's say, stationary in the universe, and we're, like, moving towards it. Okay, so we're going, let's say we're going 1,000 miles per hour. What is that in meters per second? Yeah, we're going about 500 meters per second. It's like 400 something. But we're going 500 meters per second. And what's the fastest you can run the 100-meter dash? Is it 10 seconds? Is it 100 meters in 10 seconds? And so that means you're going 10 meters per second. All right, so this person is going, let's say, 510 meters per second, and this person's slower. They're going 509 meters per second. Okay, so this is one of those where you're just like, let's not do that, and let's just say this person is moving 10 meters per second, and this person is moving 9 meters per second. You know what I mean? And that's typically from the grandstand, that's what you're going to be seeing. But you could also, now, let's see. Yeah, for this one you can do this because those two runners are going to be starting at the same distance, and then as they go, one's going to be going faster and the other is going to be slower. So if you take the grandstands out of it, you take the Earth out of the equation, and then sometimes I like to do this. Let's say these two runners are just in outer space, like a video game or something, like they're the only two things in the universe, and you just programmed them to run in that direction, and you're just like God looking down on them. Nothing else exists, but you're just making these two, you know, humans. You know, they don't know they're robots, but they're robots, and you make them run. You make them run. You know what I mean? And they think they're running this direction, but you know what I mean? You're like the God figure that, you know, I don't know. You actually just have, like, you just follow them like this, so they feel like they're running in this direction, but honestly, you're just looking at them, and then you're just gonna, you know, keep an eye on the slower one. So let's say this is the slower one, this is the faster one, and, you know, yeah, so like if you're just a drone, if you're a drone and you're just following the slower one with a camera, what you would see is just the faster one slowly moving. So this faster one would be moving 1 meters per second. And because the backdrop is just the blankness of universe, you know, there's nothing to compare it to. So this person's not moving. They're going 0 meters per second. But this person is actually just moving 1 meter per second. So there's 3 different ways to look at relative rates, and they're all the same. You know, 510, 509, 10, and 9. This would be the traditional race that we would see. Or, I like this example of, like, putting them as the only things in the universe, but I'm glad I had to think about this just a little bit more. It's like the drone is only, you know, fixed on the one thing. And this happens in physics a lot, where you're just like, hey, you're going to have a reference frame fixed to a moving object. And as long as that moving object has constant velocity and no change in direction, then that is an inertial reference frame. I don't even know. I'm just saying definitions that I can't back up with more, but it doesn't change. That's a good thing. If you're in an inertial reference frame, you're going to get accurate answers. If you're in a non-inertial reference, I don't know. But all right, back to the problem. All right, hell yeah. So from that, we can kind of take this, we'll do it the longer way. But so what's the difference between the motorcycle and the car? So let's do this. We're going to go alpha m minus alpha c, and that's going to be 22.2 minus 16.6. So we get the difference is going to be 5.5 repeat meters per second. So now, I mean, the answer is just now going to be actually very easy for me to see. But we're gonna go a slower process of just kind of chunking it and see if we can do a guess. But yeah, let's do the slower process. But even just right now, you should be able to throw this into your calculator. Like, didn't we just find a distance of 2,000 meters? And the motorcycle is going to be catching, the motorcycles be going faster. It'd be like if this race, if this is the slower person and this is the faster person, let's say the slower person was 2,000 meters over here, and now you had to start the race. How long before this person just gets to there? And then, we said in this example, the relative velocity between these two was 1 meter per second. We can treat this person as they're fixed, and so it's going to take 2,000 seconds. Cool. So this one is going to take, and then let's use units are the equation. So we have meters per second, and then we have meters here. What do we want? We want time in seconds. Seconds is downstairs in this, so we have to probably, take this and put it, take this meters and divide it by meters per second. Meters cancel, seconds pops upstairs. Just so units are the equation. We do that a lot. So cool. So we would take the 5.5 and then divide, what would we do? Take the 2,000 meters and then divide it by 5.5. So 2,000 divided by that answer, that should give us, so it's going to take 360 seconds divided by 60. It's going to take 6 minutes. But let's say I want to, Let's say I felt like there was a little bit of, maybe I messed up. Maybe I, doing these relative velocities, I messed up. So I do know that we have a 2,000 meter head start. So let's, so this distance is going to be 2,000 meters. I know that the car is going to be going 16.6 meters per second, and that's C. And then the motorcycle is going to be going 22.2 meters per second. Okay, hell yeah. And the answer that we got was like 3,600 seconds. So let's use my strategy of just running this for a second. And so, so the motorcycle is here. 2,000 meters away is the car. And I do like this approach because I find it the most difficult. It's being okay with doing a bunch of calculations. That's it. You know what I mean? Can I do 10 calculations and not lose my mind? I don't think most people can. I think from a math perspective, people just want the equation that solves for the answer, and they want to do that once. But even my brother is doing like, like wave functions, or like, he's into quantum physics, and he does lasers and stuff. And we'll try to get there. Probably not. But some of his problems don't have specific equations where you have to use an iterative process. You have to, so that's all we're going to do right now. And this comes up so much, and it's so fascinating that you can do an iterative process for such basic problems. And then you realize that these problems are like, are they derivatives? Like, what's that term? Differential equations? Alright, yeah, let's see if any of the words that came out of my mouth we're going to show. Okay, so, we're going to use that run it for 1 second. Run it for 1 second. So after 1 second, what happens? The motorcycle, we're just going to assume it has instantaneous speed, but is going 22 meters per second. So after 1 second, the motorcycle is 22.2 meters. Cool. The car is now 2,116.6. Hell yeah. That's after 1 second. And then so this is where I would do this a few times. I would do this at least 3 times and then realize, oh, I could do this in Excel, like do an Excel spreadsheet. And then this would be the most intuitive way to get the right answer. Okay, hell yeah. So, alright, so then this is after time is equal to 1 second. After time is equal to 2 seconds, this is going to be, so we're going to go 2 seconds. This is going to be 44.4 meters, and then this is going to be 2,000 alpha C times 2. This is going to be 2,033.3. Okay, and then so, you know what I mean. We can stop here. Let's take the difference. So right here, the difference between 0 meters at time is equal to 0, and time is equal to, yeah, we're going to say the head start was t is equal to negative 2 minutes. You know what I mean? Or t is equal to negative, what did we say, 120 seconds. I'm going to say t is equal to 0 is when the motorcycle starts moving from the police station. Okay, so the distance between the car and the motorcycle is 2,000. So let's see after 1 second. And this is for problems that involve change. This is so critical to, like, hey, run it for a second, and then did you notice any difference? And so what we see is that we have 2,000 plus alpha C. I'm going to store that as alpha B. This is going to be the B column. And then we have alpha M stored as alpha A. So this is the A column. So we're going to have this 2016 minus 22.2. So alpha B minus alpha A. And what do we find? We get 1,994.4 meters. So cool. What do we notice? That distance is closing. Hell yeah. And we'll do it again. So we're going to do 2,000 plus 2 alpha C. Store that as alpha B. And then 2 times alpha M. Store that as alpha A. And then we're going to go alpha B minus alpha... alpha B minus alpha A. And hell yeah. So after 2 seconds, we have 1,988. Hell yeah, I'm popular. And cool, the distance is closing. And so, no human on Earth is going to just keep writing this out second after second. You'd have to do this, you'd have to, manually do a table 360 times. But hell yeah, let me run up to Excel. Don't want to do that. I think for this problem we can kind of see that it would work out. Let me take a pause. Alright, hell yeah. Let's play around with this, because I need to stop stuttering, but I ran it for a second. Let's run it for 10 seconds, so let's go from time is equal to 0 just to all the way to time is equal to 10. And what we see in this problem is that we have constant velocities. And so for a problem like this, we will always get the right answer, even if we take a big change in time. But even if there was an acceleration, the velocities were changing, and we ran it for a second, we might get an approximate... You're going to be off, but who cares? Like, if the whole part of differentiation is, where velocity is change in position, change in time, as change in time is the limit, as this goes to 0. As this approaches 0, you know what I mean? But 1 second might be close enough to 0 where you get an accurate answer anyway. And it just happens because there's going to be no change in velocity, this is going to give us an accurate answer. But let's run it 10 seconds. What do we find? We find that the car is going, so we move this decimal place 1, so the car is 2,166 meters. The motorcycle is, move this decimal place 1, the motorcycle is 222. I don't want to do this in my head, but we got 4, 4, and then this goes down to 19 meters. Okay, so even after 10 seconds, we're improving. Let's run it for 100 seconds. Cool, so what would that be? The car is going to be 2,000 plus 1, 2. Okay, so the car is going to be 3,666 because that's going to be adding, move this decimal place 2. That's going to be how far the car is now moved. And then the motorcycle moved this decimal place 2, and that's how far the motorcycle was. So here's where the car is, here's where the motorcycle was. They're not the same. Am I doing this right? Hell yeah. Because the car is 2,000 plus this, and then the motorcycle is, I'm saying that wrong. The car is 2,000 meters plus this times a time of 100 seconds. Hell yeah. But yeah, this should be a little bit better. So we have 4, 4, 4, 1. Okay, you know what I mean? So it's better. So let's do time is equal to 1,000. And then this, we should get a negative number. The motorcycle should just be way past, and let's see if it is. Because this at least gets us in the ballpark, to be like, hey, was 360 seconds fairly close. We hope it's the right answer, but we're trying to just double check our answer. Alright, so after 1,000 seconds, I moved this decimal place 1, 2, 3. So it's hard for me to see. But we have this plus 2,000. So I'm going to have 18,666. The motorcycle is going to be this. The motorcycle started at 0 meters. Times this times 1,000 is 1, 2, 3. That's minus 2, 2, 2, 2, 2. And then, so yeah, we have a negative number. So we have 18,666 minus 2, 2, 2, 2. Alright, hell yeah. And we're going to get this answer, but I apologize because my camera was on autofocus, so it's probably just focusing in and out. That sucks. But anyway, so keep moving on. So the motorcycle is now, the difference, the motorcycle, if this is a negative number, it means the motorcycle's past where the car was. The motorcycle overtook the speeding car by 3,556 meters. So, hell yeah. Cool. So, yeah. Now I'm going to think about this just a little bit to be like, hey, can we solve this from an equation perspective? Because, one, we should be able to just come up with an equation for the distance, if this is an x, y, does this even make sense? No, this doesn't make sense. It's more time. If we have, you could do xt, because if you say the car is going to be 2,000 meters, when is it at 2,000 meters? Well, we're going to say that's maybe time. But yeah, that's the interesting thing. So let's kind of play around with this. I think that's the hardest part about kinematics. We're so used to be like, hey, if I say this is the xy coordinate, the y coordinate is air, and then the x coordinate is some distance along the ground, and then here is the surface of the earth, we can have like a setting sun and mountains and stuff like that, but here is the speeding car, and then here is, usually pretty good at drawing bikes. Hell yeah. So then here is the motorcycle trying to catch the car. And but with kinematics, we're always doing things in, time. It's like at t is equal to 0 seconds, where is the position? So, you know what I mean? Position, what is the position at t is equal to 0? So you can maybe say at position where t is equal to 0, what is that? You know what I mean? And then so we maybe we still want to have x along this because that makes sense. This is the ground. And, I'm going to say this is 2,000 meters. And here's the police station at 0 meters. And then I have to have some sort of time on this. This is time. And then we could have negative time. And positive time. So now I have to, it makes the most sense to be like, hey, at t is equal to 0 is when the motorcycle starts to leave. And at t is equal to 0, it's already given that car the 2-minute head start. So at time is equal to 0, the car is already at 2,000 meters. And now we need to figure out what this looks like, because even for this car, it's kind of weird to even graph this, because so the car at time is equal to 0 is 2,000 meters. Let's say at time is equal to, and we already did this, time is equal to 1 second. Where's the car? The car is going 16.6 meters per second. So now the car is, so at time is equal to 1 second, the car is there. So the xy coordinate on the car is going to be the x coordinate and then the t coordinate. And so we have 2,116.6, and then the time is going to be 1 second. So there's meters and there's seconds, so that is the coordinate of the car. And we know that that is going to be kind of the same. It's going to be a linear line, so that's what that's going to look like. Alright, hell yeah. And so I think graphically is probably the easier way before even getting this equation. This equation is just a y equals, it's just a y is equal to mx plus b, where, how do you solve a y is equal to mx plus b? We'll get to that in a sec. We know it. We know an x coordinate. We know a y coordinate. If we knew the slope, then we could figure out b. B is just y minus mx. I need some more ice water. Alright, hell yeah. But stuff like that is just like, I hate little stuff like this where you're just like, oh man, it's like so hard to even find the equation of a line. It makes you feel stupid. Anyway, okay, so, and the slope of this is going to be the velocity, even if you can't, see that, like, who cares? But if I did time is equal to 2 seconds, well, aren't we just, 2,000, whoa. Calculator's going to die. Alpha C times 2. Aren't we just 2,033.3 meters? And then so we just increased in this direction. So our run is going to be 16.6 meters. Our rise is going to be 1 second. So then our slope is going to be rise over run, which is going to be is that right? Rise over run? I guess so. Yep, so we're going to have 1 divided by 6.6. 16.6. And what was 16.6, repeat? We said that's going to be 100 divided by 6. Is that right? 100 divided by 6. So the inverse of that, this is 1 divided by 100 divided by 6. That's going to be 6 divided by 100. So the slope on this is 6 divided by 100. So cool. So we know the slope is going to be 6 divided by 100. Okay, let's do the motorcycle, because I feel like I'm fading fast. The motorcycle is going to be at time is equal to 0. It's going to be at distance 0. But this slope, they're going to intersect, right? Because at some time, if these two cross paths, let's say this cross paths right there. There's going to be a time-oriented, there's going to be a distance that happens, and there's going to be a time that happens. There's going to be a unique, kind of solution, and that's going to happen once, and we just saw that, hey, they're going to be side by side, but if the motorcycle keeps going at that higher speed, it's just going to go on forever. Alright, hell yeah. So just intuitively, this slope has to be a less slope, but let's talk about that, because we said that after t is equal to 1 second, it's going to be at 22 meters. Yeah, so we're going to go this way a little bit farther than this. This, we only went 16.6 every second. You know, our rise was 1. So we're going to go 22.2 and then up 1. And what's 22.2 as a fraction? I totally even forget. But we can... Let's do divided by 2. Let's get that fraction. Hola. Oh, it's not doing it. Yeah, what? I'd have no idea. What was it? It was 80 times 1,000 divided by 3,600. Cool. And then what is that? That's 200 divided by 9. Alright, hell yeah. So this is 200 divided by 9 is the run. The rise is 1. So we're going to have a slope. The slope of this is going to be 9 by 200. And there you go. And so this is going to have a 0, 0. And then so the if we solve for b, b is going to be 0 here, 0 here, and then it doesn't really matter. This equation, b is 0. So this equation is going to be y is equal to the slope. This is going to be 9 200x. And so that's going to be the y of the motorcycle, x of the motorcycle. Cool. This, what was the b? The b was going to be choose any point that we know. We know the initial point. Our y is our t. You know what I mean? So y is, shoot. You know what I mean? This is kind of like your x, y. We're just calling it the variable time. I want to get done with this video so much faster. Anyway, so to solve for, what are we solving for? Just the y-intercept, that's all. It's going to be negative, so hopefully it becomes negative. And when time is equal to 0, so this point is going to be 2,000, 0. Cool. So it's going to be minus the slope here, what did we say it was? Is going to be 6 minus 6 divided by 100. And then the x is going to be 2,000. Cool. So we're going to have, this is going to be 2 zeros cancel. This becomes 120. So b is equal to negative 120. I could be off just a little bit on the numbers on there, but I think we're good. And then so the y equation for this, we have y of the car is equal to the slope 6 divided by 100. Hell yeah, the x of the car. And then so here's our two equations. And then the question is, you know what I mean? When and then so yeah, and then so the y value is time, so we should just write it. It's just so easy for me to be like y is equal to mx plus b, and then, you know, the x is going to be the x direction, but the y is going to be time. And so let's do these again. So we have time for the motorcycle is 9 200 position of the motorcycle. And then we have time for the car is 6 100 position of the car. From a mathematical perspective, it says when the position of the car is equal to the position of the motorcycle. See how that's harder to see, like just from a mathematical perspective? It's just, I don't see that, you know, just from an equation-based perspective. Like if that rings bells to you, cool. Like if you can just see that intuitively, I think it's difficult. I think that's the hard part to see. But hell yeah. So then, even in our equations, you know, we should, let's write them one more time. Tm, 9 200, xm, and then we have time of the car, 6 100, position of the car. And then we have position of the motorcycle is going to be equal to the position of the car. So those are our three equations. To set these equal, you know what I mean, we need to maybe solve this just for xm. So all that does is take the 200 upstairs. Cool, so we did that. To solve for position of the car, we're going to take the 100 upstairs, 6 downstairs. So position of the car is going to be 100 divided by 6 times the time of the car. And now we can plug these two equations into this equation. And then so we have 200 divided by 9 time for the... is this even going to be right? I have no idea if this is going to be right. 100 divided by 6 time of the... What are we solving for? I feel like, aren't these times going to be the same? Am I getting this wrong? No, I'm not getting this wrong. It's just the fact that, yes, the time of the motorcycle is going to be the same time as the time of the car. Yeah, so there's two more yeah, that's what we have. And then I can just say this time is just a generic time, and we can say that it could be time meet. You could always put as many, you know, like subscripts on. But now we can say we have 200 divided by 9 time that these two vehicles will meet or be side by side, times 6. And so I'm using this subscript time meet to be time side by side, which is what they want for the problem. Cool. So, but don't those just cancel? Oh, this sucks. So I think I need to, where did I go wrong on this? Because these are two equations, and they should have a solution, one solution. Yeah, I need to take a pause. Sorry about that. Alright, hell yeah. But this is where solving things from a pure mathematical perspective is just like, I don't know, I probably made a mistake in here. So let's not, you know what I mean? We got two equations. I hate when I make a mistake and I feel like I need to start completely over. Don't do that. So let's plug both of, oh, damn. Yeah, y is equal to mx plus b. So, my bad. Yeah, so I caught my mistake. We just solved for... This equation is y is equal to mx plus b. And what is this? This is the car. So this has to be minus 120. And now we should be money, honey. Okay, so, yeah. So, let's see. We need to go from here up. Yeah, we probably... And I don't have this written one more time. I don't think we need to. So yeah, let's jam. That's the hardest thing about making a mistake. It feels like you can just get derailed, but we already found the solution. So just gut it up and let's go for it. So which one? Y is equal to mx plus b. The motorcycle doesn't have anything. So I'm going to say motorcycle is T motorcycle 9 by 200. Position of the motorcycle. So that's that equation. And I didn't want to write it twice. So yes, y is equal to mx plus b. Motorcycle starts at 0 meters. At time is equal to 0. And yeah, we're just saying that the car starts when the car passed the police station, it was negative 120 seconds, which we're saying 2 minutes ago. You know what I mean? So that's kind of where that comes from. Okay, so the time for the car, which is the y is equal to mx plus b, is going to be this equation. So we have 6 divided by 100, position of the car minus 120. Hell yeah. Now we have position of the motorcycle is going to be position of the car. And now we can solve this for, this is going to be 200 divided by 9, time of the motorcycle. We need to solve this for the position of the car. So that's going to be time of the car plus 120. And then we're going to take this, and then we have 100 upstairs, 6 downstairs. And that should do it. Hell yeah. And then so that's going to be the position of the car. So now these two equations are equal. And but we have that third equation, the fact that the time for the motorcycle is going to be the same time as the car. They're in the same, yep, hell yeah. Cool. So I'm just going to say that this is just a generic t, and I'm going to take this 200 divided by 9t is equal to this. And I'm going to FOIL this through, so we have 100 divided by 6t, and then we have plus 100 divided by 6 times 120. Now we can, start solving this. And let's just use our calculator, because my brain is toast. So 200 divided by 9 minus 100 divided by 6. Fraction that up, and we got 50 divided by 9t on this side is equal to, we have 100 times 120 divided by 6. That's going to be 2,000. And you see we have that same thing happening where we have time is going to be 2,000 meters divided by 5.5 meters per second. Seconds is going to pop upstairs because 50 divided by 9 is that 5.5 repeat. Hell yeah. So our time is going to be 2,000 times 9 divided by 50. 2,000 times 9 divided by 50 is time of 360 seconds. Hell yeah. Okay, so we did it a bunch of different ways. This was a good one for my first one back. Because, the only thing that I didn't do was it in Excel. Like the second I can run this for a second and see a small change, then hell yeah, run it in Excel. And then, especially for things where accelerations are involved, because then you're not going to get an accurate answer by running it for a second, assuming that things are going to be constant for a second, and they're not. Every second things are going to change. So, you can run it for a second and then change your parameters based on the new locations, the new the new velocities that things are traveling. And so, hell yeah. So I think that's such a useful way to solve. And then it shows you that velocity, even though you're doing velocity problems that are just, intuitive. I don't know if this is intuitive, but you can just multiply. Like we said, if you're going like 60 miles per hour, let's change it to 2 hours. That's 60 times 2. 60 miles per hour times 2 hours. Yeah, you went 120 miles. You just multiply those two things together. And that's with constant velocity. But hell yeah, if you're going to change your velocity, well then, yeah, things are a little bit trickier. Okay, hell yeah. So, I did it. I'm back. Yeah, hell yeah. This was fun. I'm glad I did it. You know what I mean? It's time for me to go to bed. But hell yeah, this was a nice little nightcap. So thanks for joining me. Hell yeah.